Well, so I will talk to you about what I'm doing. Like right now, read more or less just the idea, not go so technical. So I do alternative climate models with fuzzy logic systems. So what is this? So what is a model and what is a system? So here the system is just a mountain, a hiker. So how we model it? Well, this is like pretty easy. Is maybe just how much he walked and then how steep is the slope. So with the graph, maybe look something like this. Here is the steps that he had made, and here is the hiker's altitude. So this is a model, an easy model, right? Then they're like going to a more complex, let's say, a person's growing process. What depends of a growing process? Well, maybe it depends on the age, the nutrients also, what else, the exercise maybe. And it has a variable that is kind of random, if we can see it like this, which is genetics. So maybe this, the mathematical expression of how we can model this growing process. I just invented this, don't believe, please, but it's a little bit more complicated. So maybe the height of the person or the how the growing process is equal, the exercise, power to the n minus g, genetics, power to the a, or something like that. And how we would see the graph, maybe something like this, right? Here we are babies, and then we start to grow up, maybe when we are like 9 years old until we are like 18, and then our height just goes to this limit, right? So how we model the climate, or let's say surface temperature? Well, surface temperature depends on a lot of variables. Like, let's say if we want to know the surface temperature or the temperature of this cube that is here, this is the Earth, which we see it like we can see it like divided in atmospheric layers and in latitude and longitudinal measures. So yes, if we want to know what is the temperature here, well, it will depend on what is the altitude, the mean winds of the global the global winds. Maybe they carry some heat or some cold. What is the radiation here? Some atmospheric oscillations, ocean oscillations, solar cycles, greenhouse gases, a lot of stuff that it's really kind of impossible to put it in one equation as the expressions that we saw in the last slide. And how the graph would look like something like this. So really complicated to have an equation that we can solve. And well, it's even more complicated to solve it for all these cubes in certain period of time, and then imagine just to project to 1 year or 10 years or 100 years. So this is really complicated. Just a few research groups in the world, like 5 or 6, have a global circulation model or an Earth system model that can solve this. You need a supercomputer as the one that you see here, and it takes a lot of time, a lot of research, and a lot of money and everything. And well, it's a great job, but what I'm doing is an alternative modeling to try to emulate or to be similar or to have some results that actually we can use it, like in real life. So, okay. Yes, so I do this alternative modeling because climate change needs urgent action. Simple models are easy to understand for decision makers and for climatologists as well. Maybe sometimes are really difficult. And well, yes, so we use this. As you can see there, the surface temperature is that, the bars, the blue and red ones. And it's very similar to the CO2 concentration. So in climate change, we are focusing most of it in the CO2 concentration, how it will affect the whole climate. So, okay, let's see the climate as an engine or something, like a set of thousands of gears, right? Every one of it is like pressure gradients. El Niño, have you heard about that? It's okay. It's an ocean oscillation, some solar cycles, ocean oscillations, wind transference, greenhouse gases, humidity gradients, topography. It's a lot of gears that they move the climate and actually give us like what is the climate. And maybe the graph that we see, it's very complicated as the one that we saw in the first slide. So it goes something like this, right? The real climate state. So what we do in these simple models, we fix all these gears into a position, and then we don't let them move, so they are fixed. But then we let the gear of greenhouse gases free, so it can move. So then all these gears are fixed except the greenhouse gases. So far, does it make sense? Okay. So then it becomes very simple because it's just one variable that depends of all the climate model, and then maybe it gives us a simple line like the one that we see here. Then we move again all the gears to another climate state, and then we let move again the greenhouse gas, and maybe we obtain another simple model. And again, we move all the gears to another possible climate state, and then we create another simple model. So with these 3 or more simple models, what we do is to actually, in fact, we measure what is like the climate state right here. We measure all the variables and see, well, here the gear of ocean is like this. Maybe the gear of the wind is something like this, and we measure all the gears, and then we see, okay, this climate state, it's very similar to, let's say, this, and a very little similar to this. So what we do is to kind of merge these simple models using something that is called fuzzy logic, which is not common or not classical mathematics. In fuzzy logic, every statement, every equation has a certain degree of truthness. So this way we do we add this model with this, but in a fuzzy way. So we can say, okay, let's say that the temperature is the result of this. Like it will be very much likely like this, but also a little bit like this. This is a fuzzy equation, like using these kind of ideas of very much like this and a little bit. We can put it into a mathematical equation. Maybe it sounds a little bit not mathematical, but it is. And then we see that the combination of these simple models maybe give us something very similar to the real climate models. So, well, this is just how it looks like in a code. And then, well, this is my thesis work, which these simple models. Here we can see the temperature in red, the observations. And here is a model that I created, which the first years, as we can see, well, it's very similar to the actual temperature. This is the global surface temperature, okay? And then we start. Well, I start again this model from 1998, and then it also like goes into this certainty or into this range of temperature, right? So well, it actually works good, and it's very simple. You run it like in 10 seconds in my laptop. So that is awesome. Then these are some projections. This is some scenarios that experts in the economic field or the social sciences do. So they say like, well, maybe in the future we can develop like this or like this or like this, and then we just put it in a model and it gives us that temperature. And yes, so well, we think in a higher degree of significance and less precision. This is fuzzy logic. So what is this? When you ask a question to a friend that he came from outside, and you ask him like, is it cold outside? You don't want to know what is the precise temperature with Celsius and decimals or whatever. You just want to see if you should bring a sweater or not. It's the same with climate change. Like, what we want to do is climate changing, how it will affect my coast. I don't want to know how many meters with centimeters it will rise the sea level. I want to know if I can make a house here or something. Also, how it will affect poverty. Governments don't want to know it will be one more poor person. That doesn't make sense for the actual decision makers, right? It goes with more significance and less precision. This is what fuzzy logic does. And well, also some examples like how it will affect food production, for example. And well, this is what we do. We do not try to model every year here, but like the whole system with certain significance. Well, that's all, my friends. Thank you.